Okay, hello people. So in this video, we're going to be talking about the implementation of the thread pool in Go. And this is the continuation of the previous video where I was talking about the thread safe queue. So if you didn't watch that, I highly recommend doing that because that would be a prerequisite to this video because I use this thread safe queue as a subcomponent of the worker pool. Right. As usual, I will go through the code and try to explain what I've done and how it works, where it can be used, etc. And I will put a link in the description so you can take a look at the code and explore it on your own. Yeah, just one thing that I want to mention is that I'm only studying Golang. I'm not like a experienced programmer by far at all. So the things, the way how I have done it, I would imagine that an experienced Golang programmer would do it completely differently, using channels and Go routines instead of using thread safe queues. But this is my implementation and I've learned a lot while doing that, so I will try to share my experience and how it all works together. I will briefly mention the queue and we go through the code as well, and then we jump straight to thread pool. So the queue is like a regular data structure which has some indices and then the mutex because it is thread safe, and this is a circular queue, so which means that whatever if you append element, for example, to the end, it will wrap to the beginning, and it grows as well. So if you run out of capacity, we will double the capacity using the grow function. So I have a queue here. You can check it out in the repo, and I have tests for the queue that I have implemented. There are quite a lot of them. Probably like it's not necessary to cover that much, but I want to like play around with it and try and cover all the cases. Yes, I will mention that there is still one problem that I don't know how to solve, and that is regarding logging in the thread, say in the concurrent context, because currently I disabled all the logging in the thread pool because if I enable logging, it will block. And that is not the problem on the thread pool itself. It just I don't know how to implement logging in the concurrent way, so it's like a thread safe. So it operates in a concurrent context, but we'll get to it later, and I will show you what I use for logging, and we will cover that as well. Thread pool. Yeah, I have it on the right side, and let me double check whether I'm still recording because I don't want to lose the progress. Okay, so the thread pool, I have like a couple of core data structures here, and so the first one is like this is just an auxiliary data type which is used for accumulating the metrics and then displaying the metrics. So for example, there are some fields like tasks submitted, tasks done, tasks queued, spawned Go routines, and finished Go routines. So as our pool operates, I record all those like events, and that would be our metrics, and then we can retrieve the metrics, and by the end of the pool execution and take a look whether everything was correct or not. So just some it mainly used for debugging purposes, but I want to take a look. I want to know exactly how much tasks submitted how many tasks were submitted, how many we executed already, and etc. etc. So basically, it's the way of like retrieving the information. I think it can be used like from in the client server application, where you have to take a look at the bandwidth and how many messages or bytes were transferred, so things like that. So it's pretty similar. And then the core data type is the thread pool, and it has like I will go through all the fields one by one. So it has max threads, which is the maximum amount of go routines that you can execute, because we cannot like execute. So if you submit, for example, 1,000 tasks, we cannot execute 1,000 go routine, because that will be killful, and that's not how thread pool should be implemented. It should limit the amount of go routines or threads, if you are talking about C++, for example, and basically, if some of the go routines have finished, we just spawn the new ones. But we will get to it later in the main, like in the main function of the thread pool. I have 3 queues here, and again, probably like the implementation should be way more simpler, or maybe, I don't know really, but the way I did it is using the thread safe queues, and I try to play around with channels, and I know how to implement it, but I haven't gotten to that yet. So the first queue is for submission. So whatever task, whatever, like when we submit a task, it is pushed into a submit queue, and the thread function is just a type alias for function which doesn't take any parameters and has no return value. So all the tasks are represented in that form, and I will show you later how to get like the return data from the function, and how to supply data to that function so it has something to operate on actually. And we have a waiting queue here, and what it does is basically when we still have some tasks in the submit queue, and we cannot spawn an additional workers or threads or go routines, we push all the upcoming tasks into a waiting queue. And then what we do is we pull from the waiting queue first until it's empty, and then we come back, and only then we get to submission queue. And the work queue. And the work queue is basically an actual, the most important bit is we use it for polling the tasks. So basically all the workers, we spawn 16 or 32 workers, and what they're doing is that they are constantly looping and trying to retrieve like so basically what they do is they are constantly monitoring the work queue, and if there are some elements of, they just get the task from the work queue and they execute it. Otherwise they just quit. WG is sync wait group, so that's basically used for synchronization. The same can be achieved with channels. So you execute a go routine in the middle, and I can show you. So yeah, you will find it in the code, but basically what it does is you execute some function, and you execute some function, and then you say wg add 1, so you're saying how many go routines you have spawned, and you will wait for them, right, to complete. And here you would have to use done, and here is some code to execute. here is some code to execute, and that's it. So yes, we can go further, and here we have a done channel, and what we use a done channel for is basically to wait for all the already submitted tasks to complete. And this is important because right after we call pool wait, no more tasks could be submitted, and all the tasks that were submitted before will be run until their completion. Thread count is basically some I will show you later, but it's a variable which will be accessed atomically, and this is amount of go routines that we executed or threads, and yeah, metrics I explained before. Waiting, whether the queue is in the waiting state or not. Blocked is whether, like, if we are in the waiting queue, that means that the submission of tasks is blocked, so no more tasks could be submitted. Yes. And logger, I explained the problem here, but as I said you before, and we'll get to it later, I have a lot of logging here just so I can see what happens. And the problem with it is that the logger that I'm using currently is either cannot be used in the multi-threaded context, or I don't know how to do that. So I wrote that, and that's why I have this logs enabled option here, because by default all the logs are disabled. So, and here is like one more command. As long as, like, as soon as I figure out how to deal with this issue, I will enable all the logs, but for now they are disabled. Yes, so logs enabled flag should be removed once I figure out how to do concurrent logging, because currently with login enabled, some tasks would block forever due to the fact that the writer is not protected by a mutex, I would assume, and prohibits simultaneous writes. Sometimes all the logs could be displayed correctly without blocking, so in that case all the tasks will succeed, but sometimes they don't. Alright, so let's jump to the function for pool creation, and maybe I can put like some tasks on the left side so we can see how it works. So for example, this task, so we created a pool. Oh no, that's not here. So we use the new pool function, and we create like 16. We specify 16 here, which means that this is the maximum number of threads that we want to execute. And here I do some basic filtering. If like the number of threads exceeds some number, the maximum number of threads that can be executed on this machine, which I check with runtime number of CPUs. Then I set it to this value, otherwise I keep it. And the same applies about 0, I assume as well. So here I create a thread pool, I specify all the options, I create the logger, we'll get to it later, I specify the maximum amount of threads, and then we have 1, 2, 3 queues. Yeah, basically submission, work, and waiting queue, they probably have to be put in different orders. Oops. And they have to be put in different orders, like this. In the order of declaration, then syn group, done channel, and yeah. And then I spawn the process task function in a separate coroutine, and we'll get to it later as well. So the submit task is used for submitting tasks to the pool. As you can see here, we iterate in a loop, and we invoke pool submit task, and then we specify a task that we want to submit here. Right? that's it. Okay. Yes, so we submit the task. We have some logging here. If the task is equal to nil, we just don't submit it. And if the like the queue is blocked, if the pool is blocked, we cannot submit tasks anymore. So we just return. Here just basic logging, and then we push the task in the submit queue, and we increment the matrix atomically. This is the main function which is responsible for processing, like this is the core logic of the thread pool, and it's a bit convoluted, but this is the best I could come up with, and I could have simplified it and used less queues, but I wanted to follow like the clear structure and reduce the queue contention when a lot of tasks are submitted into the same queue and a lot of tasks are popped from the same queue. So running variable, we check whether we are in the running state or not, basically, and we check whether the waiting queue is empty. If the waiting queue is empty, okay. We create the tasks, just a declaration, and then we're trying to pop the task from a queue, from the waiting queue, and we do it until it will be empty, right? Then we push the tasks into work queue, and then we check the submission queue, whether it has something in it, whether the tasks were submitted, and we push that. We try to pop that as well. And probably we could have used the same variable, but for clarity, I will keep it like this. So we try pop the tasks from the submission queue and we put it into the waiting queue, so we can iterate over it again. Right. If the waiting queue is empty, we proceed to the submission queue. We pop the element, and we check whether the amount of spawned workers is less than maximum amount of allowed workers or go times, right? That can be executed simultaneously. We push the element into the work queue, and we spawn a new worker because we are allowed to do so, right? Because we still below our limit. We spawn the worker or the go time, and then we update some metrics just to keep track of how many workers we spawn so far and things like that. Otherwise, if we exceeded the amount of maximum threads, what we do is we just put the task into a waiting queue and we update metrics. So then that task can be later received from the waiting queue and processed accordingly. Okay. If atomic, okay, so in the else statement, if the submission queue is empty, we check to see whether the waiting doesn't equal to 0, and I assume that's because, yes, okay. We need to check whether we are in the waiting state. And if it doesn't equal to 0, which means that we are not in the waiting state anymore, we just return false, and we which means that we check if we are in the waiting state. And again, I will say it one more time, waiting state implies that no more tasks can be submitted to the pool, and we have to finish and wait for all those tasks that were submitted before, right? So we set to false and we exit the loop. We wait for all the executed early go routines to complete, and then we close the done channel, which means that we unblock this line, because it's like Go channels is a synchronization mechanism, right? That this line would block until we either send a message, because this is a receive operation, and this would block until a corresponding send operation will be executed in a separate Go routine, or we close the channel, which signals that we can no longer send elements to that channel, but all the elements that were received, that were sent before the channel was closed, will be still received. So this line will unblock. And yes, so the next function is like debug get metrics. I just, for debugging purposes to get metrics, I use it for testing, so I don't like access pool.metrics.something. I just get the metrics back and then I operate on metrics itself. Then a worker is actually the function which executes tasks. And here we have some logging, but what we do is we defer done statement, which signifies that this Go routine has completed, right? Because here we add the amount of Go routines we spawned, and here we say that, okay, this Go routine is completed, which decrements the counter internally, right? Yes, and we increment the thread count, and here we decrement the thread count, because here the function has already executed all the tasks because the queue is empty. So we are checking constantly in a for loop whether the queue is empty or not. We pop the task and we update the metrics and we execute an actual task. So this is where your submitted task, for example this function, starts its execution. All right, and we have the wait function, and I will mention it and I specified it in the description for the repository that any call to new pool should be augmented with a call to wait, because this is really important, and otherwise that wouldn't work. Because we won't be able to wait for all the tasks to complete. We just submit all the tasks and immediately finish. We don't wait for the tasks to do their job. So here we say that pool is blocked, which means that no more tasks can be submitted. And here is the place where we use it. If P is blocked, then we just return and do some logging. Atomic operation is basically we set the P waiting in a waiting state. We notify the pool that we are waiting for all the tasks that were submitted before for their completion. And yes, basically here we block until we receive a signal that we can shut down the system. So that's it. I have an example of how it works, and I have a couple of interesting tests that I wanted to cover. So, for example, I have here the okay, so this is like a let me just refresh my memory because I don't remember. Involved. Yes, okay, so this is like a concurrent accumulation. We submit. Yes, okay, so we populate the data with some numbers, and then we compute. So we have a big array, like a huge array, but in this case it's not that huge, it's just 4 kilobytes. 4,096 elements in the array, and we populate it with data, and then what we do is we compute the sum of all the elements in the array. So yeah, using distribute work by chunks, and and we do it concurrently. So we have a huge array, we distribute it by chunks, and we submit those chunks for the worker pool or the thread pool, and then the thread pool as tasks, and then the thread pool computes the sum of each chunk, and then we sum everything together at the end, and that's how we speed up the process of computing the sum. So instead of iterating through the whole array element by element, we just split it into chunks, submit chunks to the thread pool, and the thread pool computes the result, the sum of all those sub chunks, and we add them together. I am using here a couple of helper functions. So for example, I can take a look at this, distribute work by chunks, which basically gets the thread pool, some additional data like the channel to which we will be sending the sum of sub chunks, and the chunk size, basically how big is the size of our chunk. So if the array is, for example, 256 elements, the chunk might be 16 elements. So every single chunk consists of 16 elements, and then the whole number of elements divide by the whole number of elements we divide by 16, we get the number of chunks, and that would be equal to our tasks, right? But it can have a reminder, and for example, if the number of elements is not not divisible without the reminder by the chunk size, that we have an additional chunk and we handle it here. So we iterate over all the chunks and we submit task. So the task, what it does is just calls the compute sum function and sends the result of sub chunks into the result channel. And here is the lambda function which does it. Here is the lambda function which does it. So we iterate over from the start to the end, from the start of the chunk to the end of the chunk, and we like accumulate all the elements, and then we return their sum and send it over the channel. This is like for the remaining chunk that I mentioned before, so nothing special here. And yes, so this is it. Okay, I see that. Okay, and here we accumulate all the like the actual sum of the whole array, because we iterate through all the like entities in a channel, and we sum them together, and the total sum I should probably since this is the benchmark, I didn't introduce the assertion statement here, but I could have done that. So yeah. Another task that I have here, which is really important to me as well, and especially interesting, is I allocate a huge byte array, which is 1 gigabyte, but you can replace it with 4 gigabytes. I tested, it works correctly. Like, and you fill in the 1 gigabyte of data, or 4 gigabytes of data with random bytes, chunk by chunk, and you specify the size of a single chunk, and then we compute how many chunks do we have, and whether we have a remaining chunk as well. And we send all the results to a channel, and then we verify that And yeah, what's interesting is that I'm using like not only the function which fills in the array of bytes uses the thread pool, but the one which verifies that the data is correct uses the thread pool, because otherwise it will take forever, right? And I try to run that. I try to run that on my system without multi-threading and all, and it couldn't finish like in I don't know how many. I don't know. I don't remember how much time I was waiting, but it was quite long. But now it takes, I don't know, maybe like for a chunk of 4 gigabytes of data, it takes 8 seconds to fill in the chunk with data and to test it to verify that the data is correct. So here, what I'm doing is that, and basically I'm using show memory usage. This is a helper. This is a small helper, and yeah, let me show you. So what it does is to do. No, that's not correct. That's not what I wanted. Yes. It basically displays the memory allocation, how much memory do we consume, right? So I can see, okay, I haven't done anything, how much memory do we consume? Then I allocated like a huge array of bytes, how much memory do we consume right now, or how much memory we allocated. And then in the end, where we finished, we tested, I freed the memory manually, invoking the garbage collector, and then I execute the show mem usage function in order to see that everything was cleared and we don't have like any dangling memory or anything like that. So yeah, and the main loop is we iterate through all the chunks. I don't necessarily remember why it's -2, but yeah, because I wrote it like a long time ago. But what we do is we compute the start of the chunk and then we compute the end of the chunk. And it is a bit different if it is a remaining chunk, which is checked here in this if statement. If we have a reminder, and this is like the chunk, the last chunk, we submit the tasks differently. And what we do is we invoke the read, and this is R is the random, yeah, so I explained it here. So I create like a random generator and I seed it with some value, and then what read does is it fills in the buffer of this size, and I'm using the slice with random bytes. So it randomly generates bytes and writes them into buffer. And you see I'm using mutex unlock here because I spent a lot of time on it, and I have discovered that read operation, it cannot be used in a multi-threaded context. So read generates length p random bytes and writes them into p. It always returns length p and a nil error. Read should not be called concurrently with any other rand method. And this is really important because I've seen that, okay, since I'm using the Golang statement here, which basically checks whether we have any Go routine leaks or no, and it gave me like a huge stack and I couldn't realize why, but then I discovered that this read cannot be executed simultaneously because the buffer of data is shared, right? So yeah, we just subdivide it into chunks, and we write a bit here, we write a bit here, we write a bit here, but obviously they cannot overlap, but still the read cannot be called simultaneously. And then I submit some data, and this is only for debugging purposes. I submit the chunk itself, the starting index, the ending position, and I submit that to the channel to basically this is the way how to retrieve the data, the result of execution of your task back to the main thread. And this is the way. And I see and the same works for supplying data. You can create a channel and the task which we submit here will be constantly polling the channel and retrieving some input from the channel, processing the data, and pushing the data to the channel. Yes, and then we have p submit task. That's for the regular chunks, not for the last one, right? We still use the mutex lock and the mutex unlock, and we push like the result to the channel. Then we wait for all the we saying to the pool, okay, wait for all the submitted tasks to complete. We close the chunks channel, and then we verify that our buffer and all the chunks that we accumulated so far, they are equal. They have an equal contents, because this is used for testing purposes. Okay, and that's pretty much it. I have an example here, and what it does is, yeah, I have to uncommand some things. Probably this one, like this, FMT package. FMT package, and yes, okay. So yeah, let's start from the main function. So what do we have here is we have like a structure for options, which contains the depths and URL. So it's the example is concurrent web crawler, which you provide an URL, you provide the depths, and then it crawls the web page in the breadth first search order and receives all the URLs up to a certain depth, right? The depth too is set by default. So we specify some options, we add a flags. This is the flag for, so basically the depth and URL can be specified over the command line as a command line arguments. And yeah, so we parse in those options, and then we execute a function, traverse URL, breadth first search, concurrent. So this is the main body of the function. We push the initial URL that we have submitted, right, to a channel. Then we this is the channel which contains all URLs, and we use it for basically displaying the URLs in a separate Go routine here. So yeah, and we push the first one here as well, so it can be displayed right immediately. We create a pool, and we have a select statement. So basically what we do is we get the URLs, and URLs are submitted here. We invoke one more function. Let me grab some water because it's extremely hard for me to talk. Okay. Yes, so let's come back. So we have a for loop. Inside a for loop we have a select statement, and what it does is it has like two case statements. It has a timeout, and it receives elements coming from the URLs channel, and URLs channel is a channel of URL info structure, which is probably I should cover, contains an URL and the depths. So the depths is to which extent can we traverse this URL. So okay, we traverse this URL this URL, we receive the page, we parse the page, it has some more URLs, so that will increase the depths. We then go to those URLs, and then we retrieve more pages, we go to those URLs, etc, 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 and we traverse in the breadth first search order, right? Because we are not going like first found URL, we go to that URL, then we parse the page, the first found URL, we go to the next URL. No, we just scan through all the URLs in a single page and don't proceed further to the next one until we are done. Yes, so we receive URLs here, and if we were not receiving anything for the duration of 1 second, we break out of the loop. Yes, and at the end we just wait for all the tasks to complete, and this is our submit task function. So basically this is how I use the thread pool, right? So this is the submit task function. What it does is I use NAT HTTP package. NAT HTTP package. We get so basically we call the get we issue a get method to a specific URL, we get a response back, we parse that response, we check whether the status is okay, we get the body of the response, and we parse the body itself, and we close the body, and then we iterate over all the URLs fetched by this function, and we append them to our URLs channel, so then they can be processed further. And not only we submit them to our URLs channel, but to all URLs as well. So we have like a list of all the URLs, so we can print them here. And this function is executed on the background, so we constantly we waiting for all the upcoming URLs, and as soon as we get one, we print it out to a standard output stream, right? So we can take a look at this function, traverse HTML parse tree. Probably I should have picked a better name, but whatever. And I explicitly made the stack implementation because I didn't want to make it recursive, because right now that simplifies a lot of things. So we create a stack, and I will, like, maybe I can show you the stack firstly, and then secondly I can jump to explaining that function. And let me grab some water. So we have a structure here, and this is the stack of arbitrary type. We have account, we have data. So what we do is we have a couple of methods. I didn't define all the methods, only those which are used and those which are the most important. So the push, we push element of type T into a stack. This is how the stack grows, just regular things. If we run out of memory, we grow the stack, we double the size, the capacity, and then we copy all elements into the new buffer, and then we append the element at the end. We check whether the stack is empty, we check the size of the stack, and we try pop the element, which basically does the same as a queue, but it's not. It doesn't have any mutexes, nothing like that. It just checks whether the stack is not empty, and then we get the element back. So we get the element and we pop. We're saying that decrease the stack size. And probably what I could have done is var 0 element of type T, and Okay, as count minus 1 equals 0 element, as count minus minus. That should be data, right? So we zero the data to make sure that we don't have any garbage there. But it's not really necessary, since we maintain an index and every push or pop operation is done through the index itself. We are not operating on the data directly. So just it's not really necessary, but a good thing to have. So yeah, try pop operation, and here what we do inside the traverse HTML parse tree, we just we create a stack of HTML nodes, and because HTML node is just a link list, or a node consists of a node type and some data. So basically we have the parent, the first child, last child, and all of those are pointers. So we have to traverse that in order to get to the next node. So I push initial node into the stack. I iterate through, I loop until the stack is empty. I pop a node from the stack, and I check whether like it has an A tag, and whether this is element node and it has an A tag, and then we get all the URLs. So basically these gets all the, like, parses the HTML page and gets all the URLs back. And we append all the URLs to the slice of strings. And here what we do is we iterate. We say that, okay, if we have more nodes, we just push them onto the stack, so then they can be processed later, right? So like a child equals first child doesn't equal nil, next sibling, and then node stack push elements into the stack. So basically here we push additional nodes, elements of type pointer to HTML node, into the stack, so then they can be processed later. It's very similar to the recursive approach, but it's better because it's iterative, and you keep everything in your head and you see the clear structure of the program. So that's what it does. And to do yes, and so the application will just print the list of URLs to the standard output. Well, okay, that was a brief introduction of what I've done, and let me jump to the logging. And this is really important because I haven't figured out the way how to make it work in the thread safe, in the concurrent environment, because currently it doesn't. And I'm using 0log as a base system, and here is like the wrapper around it. So basically I have a function, create a new logger. I set up the global login level, which can be either debug, info, warning, error, fatal, panic, disable, trace. So this is a map from it's a string representation to an actual level that you can supply to set log level function, and this is basically sets a global log level, right? Yes, I introduced like a custom writer here. Yeah, and here is like the structure logger, which I was using here inside a thread pool. This is like embedding the types, so you can you don't so this is a Go feature. You don't declare a variable, a member variable. You just say the type. It's a pointer to the logger, and then you can access the logger directly. So for example, here I access the logger directly. Okay, so my current problem is that all the writes, they don't work in a concurrent environment, and so we have a console writer, right? And I thought that will solve a problem, but apparently it doesn't. I will show you later what I did. But we have a console writer, and again, I'm not the professional here. I was just experimenting with different login systems, and that's what I came up with, and what I'm trying to operate on. So console writer. We have write function, and as you can see, this function doesn't have anything like related to mutexes. It doesn't lock anything, neither, like nothing in this function is locked up, like doesn't, nothing is telling me that this function can be executed in the concurrent environment, right? So what I was trying to do, since I'm using console writer, is create a wrapper around console writer, my own writer, that uses mutexes. And basically what I did is I added like a type, new type, which has a console writer and the mutex. And whatever write method is, so I overloaded the write method because to meet the requirement of an interface, right, for the IO writer, because as you can see, new function here, it accepts IO writer, and IO writer is an interface which has a write overloaded, which has a write function with exactly the same signature as I did here. So it takes bytes and it returns number of bytes written and the error. And what I was trying to do is I was trying to a bit hack the system, but apparently it didn't work because I still get locks somewhere. Yes. So what we have is we log the mutex, we defer the unlocking the mutex, and then I was trying to call the write an actual function, but it doesn't work, and I don't know why. I thought that it will solve the problem because we lock all the calls to the write function and the close function, and and then an actual console writer write will be protected with a mutex, so that is fine, but that still didn't work. So this is the logger and how I created this logger, new logger, and then just plogger info, and that will give you a message. And here I set up some settings so the output looks nicer. By default it's JSON, but you can redirect it to a console and you can configure how it looks, etc. I will probably put a link in the description to the wrapper of the 0 log, so we can take a look. Okay, I will try to keep this video short. I have been talking already for 54 minutes, and I think I need more water. I will put a link in the description, add some useful links, and if you have any questions, please feel free to leave a comment below. I would really appreciate that. Thank you for watching.